Um, Hi everyone. I'm just checking my sound. Just checking if you can hear me. If you can just put some comments in the chat box. Hi Vincent, good to see you again. Can you hear me?
Hi, Barry. Yeah,
Hey,
I can
good.
hear you. Can you hear me?
Thank you. Oh, great. Hi Imshas, nice to meet you. All right, awesome.
Yeah, nice
I
meeting you
was
too.
just checking my sound. All right. Thanks very much for joining. Yeah, just for everyone, more especially for those who are joining us for the first time, if you can just maybe disable the sound, the notification, so that you don't get to have this disturbance when you're trying to listen to the session. So if you can just go on the settings and then just ensure that you disable sound and the notifications. Welcome to our session today. My name is Perry. I'm based in the South African office. Topic for today is HVDC Technology for Power Transmission. This is hosted by, presented by Dr. Imshas, who is also our lecturer here at EIT. However, before I hand things over to him, I just want to quickly address a couple of questions. So we do have people asking about copy of slides and the recording. So we will provide you with the recording and the slides of this session after the event. Obviously, it will be in about 2 to 3 business working days. And again, we provide a certificate of attendance. So how it works is at the end of this session, I will be providing you with the link or a QR code. You're going to have to follow that link or scan the QR code in order to request your certificate. So in other words, you need to attend the session from the beginning all the way to the end, and then at the end of this session, I will provide you with the information on how do you request your certificates. However, should you not be able to request your certificate making use of that information, unfortunately, we cannot be able to provide you with the certificate of attendance. So just make sure that you stick around all the way till to the end, and then I will share the information with you. And just an overview for those who are joining us for the first time. Just to give you some, sort of like information about who we are. So we are specialists when coming to engineering. At EIT, we specialize in strictly engineering. And I know you have like this other institution, specializing in other programs, business, marketing. But however, here at EIT, we only specialize strictly with engineering. So you'll see that we have professional certificates. Those are our 3 months professional development programs. And then we have diplomas, we have advanced diplomas, undergraduate, graduate certificates, bachelor's, master's, and our highest qualification is Doctor of Engineering, our doctorate qualification. And yes, we are industry orientated. We ensure that our study materials, our resources for students are up to date to ensure that we keep up with the technology and the trends in the industry. And then again, yes, we do offer world-class accredited education. So we just like any higher education provider in Australia. Our qualifications are created with Australian government. And then again, we have some of our programs that are recognized under 3 international engineering accords. So you get our advanced diplomas under Dublin Accords, and then you get our bachelor's under Sydney, and then our master's programs under Washington. We source our lectures from different parts of the globe. Our lectures are engineers, so our students learn from our engineers, and we provide this unique method when coming to delivering our courses. We do have interactive webinars that our students use, remote labs and simulations that they use when they doing their practicals online. And yeah, obviously, to learn more about EIT, you can always just go on our website. But at this very moment, I just want to hand things to our lecturer, and Dr. Imshaz, you can take it away, sir. Thank you.
Thank you, Barry. Thank you very much. Hi, everybody. So this is Imtiaz Madni. I'm currently based in Perth, Western Australia, and I'm working as a casual lecturer with EIT uh, from very long time, actually, 4 to 5 years now. And I teach some units related to electrical engineering and industrial automation, so bachelor's as well as master's, and I do some thesis supervision as well. As my full-time work, I am the lead electrical engineer, working in industry for power systems from very long time. I've got a PhD degree in electrical and electronics engineering from the University of Western Australia. And I worked in academia for some time and then joined the industry. So I have very diverse technical background working in R&D and as well as product development, and then in the industry working on real life projects. So there's a lot happening in Australia, same as some other, actually many other countries in the world. There is a lot of focus on energy transition these days. So I am part of that energy transition, and we have been working on several large scale renewable energy projects, so including solar farms, wind farms, and battery energy storage systems, and then distributed energy resources like microgrids. So as part of that energy transition, as you may know, that there's a lot of discussion about the grid infrastructure upgrade and replacement. So that involves the power transmission, like we can have these large scale renewable energy systems, but how do we integrate them into the existing or the new transmission network? So that's where this topic is also important, that HVDC has become very hot topic these days in terms of the new infrastructure development. So yeah, I will be talking about some overview of the HVDC. Obviously, the whole technology is a little bit um, too broad, means it has several different components to it. But I will just talk about the basics and then just give you an overview of different components and types of high voltage DC transmission. So HVDC transmission, it has become very popular in recent days because the major reason is that we have now the capability to produce high voltage DC power, whereas in the past we were limited with the voltage in terms of DC. So that's why the DC transmission was not very feasible in the past. Um, but nowadays, with the development in the power electronics field and also some material technology, so we are able to uh, do that. So we are able to um, increase the voltage. So high voltage DC power transmission is being used in variety of applications. So one of the main driver, as I mentioned earlier, is the renewable energy. So there's a lot of focus on the intercity transmission or interstate, as well as inter countries from one country to another country, because um, with the renewables energy. Some countries are really advantaged, like they have the best solar irradiance or good wind um, profile. So there are a lot of projects where the generation is happening in one country, and then the power is required to be transmitted to another country. So that's a long distance transmission. So that's where HVDC has advantage over the AC transmission, which we normally use. So HVDC also important for geographically dispersed projects, like I mentioned, solar farms, wind farms, and can help mitigate the effects of variable energy generation levels by providing a means of averaging the various changing power outputs. That means we can have several different solar farms interconnected at different location on the same transmission line, and it has minimal effect on the transmission line. Whereas in case of AC, we have to be very mindful about the synchronization of different um, generation sources into the network. Um, so HVDC is already used to bring hydropower from remote generation sites to urban centers. There are projects already developed which are uh, using HVDC. Um, so as I mentioned, with AC transmission network, the biggest challenge is the synchronization of different networks, because we need to be mindful about the frequency as well as the voltage, and so that can obviously limit our options, or we may need to do a lot of retrofitting, like external components to manage that synchronization. Whereas with HVDC, we can often connect unsynchronized networks. So that's another advantage of HVDC, that we can also use it as a linkage between unsynchronized AC power networks. So we can basically use it as a linkage between two different networks. So how it started, actually, we started off with DC power, as you may know already, that in the beginning, when electricity was discovered and the electrical transmission system was developed, that was DC powered. So Edison was working with the DC, and then there were some limitations with the DC systems, obviously. Like I mentioned, in the past, we didn't have the technology or the components required to achieve high voltage in DC systems. So they could not transmit power for more than a couple of kilometers. That means they needed to build power systems within the cities, like the generation systems within the cities or very close to their utilization points. But then Tesla introduced AC power, so that's the whole um, battle that happened at that time between Tesla and Edison. I'm sure you guys are aware of that. So the transmission distance uh, was uh, means that challenge was minimized by using AC power, because with the DC, as this transmission distance increases, voltage drops significantly due to the resistive losses, obviously. So that I squared times R loss, which is typically the resistive loss. So basically, if we wanted to send DC power for long distance, so the size of DC cable needed to be used was exceptionally high, so that was not very practicable. So with the development of AC, it became very easy to transmit power over long distances because we could use transformers to step up the voltage and send power over long distances and then step down at the usage point. So power could be transferred over long distances using AC by using those transformers that were invented by Tesla. So that's when everything switched to AC. And for a very long time, we relied on AC transmission and AC distribution system. But we know that there are challenges with the AC transmission. There are actually um, too many challenges, not just the synchronization challenges as with the renewable energy, but also typical AC power has its own challenges like some losses and inductive losses as well as the corona losses. So, um, but we didn't have the means in the past to use HVDC. So that's when nowadays we have improvements in DC systems so we can actually optimize our system to work on high voltage DC transmission rather than AC because first of all we can minimize the cost as well as the infrastructure requirements because for DC obviously we don't need that many wires and cables. So major problem that Edison could not solve was how to increase the transmission voltage of DC for transmitting power over longer distances. Um, but over the years, then we have developments in material technology as well as semiconducting and power electronic technology. So with the development of these mercury arc valves, so it became easier to convert power between AC and DC. The AC power could now be converted into DC after stepping up the voltage. So using a transformer and at the end of transmission line, then we can convert it back into AC for stepping down. So that means that we don't need to actually reinvest into all this distribution system to upgrade to DC. We can keep the AC distribution system because there is a lot of investment already into the distribution system, power going to the facilities and our homes and offices. So if we switch fully to DC, then obviously it doesn't make sense economically. So with that conversion back to AC, we can still keep using our existing distribution network. But for the long distance transmission, we can switch to HVDC. So basically, this invention of these mercury arc valves, so this made high voltage DC transmission technically feasible. And so today, HVDC technology is used as a highly efficient alternative for a huge amount of electric power transmission and for also interconnecting the power grids with different frequencies. So because we don't need to have this synchronization for the high voltage DC transmission. So if you compare HVAC to HVDC transmission, so there are several factors which we need to keep in mind. First of all is the capex, right? The capital amount which we need to spend on the infrastructure required for DC as well as for AC. So first of all, DC transmission, as I mentioned, that we don't need as many conductors for DC as for AC. For example, when we talk about AC power, typically we use three phase. So basically we need three wires for each phase, one for each phase. But with DC, we essentially don't have that issue. We just use two conductors per DC circuit, positive and negative. There is no phase and there's no phase angle difference. Um, so HVDC also allows line supporting towers to be smaller. So basically, if you're not using many conductors, so you don't need to have the larger span of the towers. And also because DC doesn't have those corona problems or other electromagnetic issues, so we can make these towers smaller and compact. So that can also save cost in terms of the tower cost. Um, so then obviously HVDC transmission line would cost lesser than a HVAC line. But with HVDC, we need to be mindful of the cost, additional cost in terms of the converter stations. So as we um, discussed that for HVDC, we need to step up the voltage and then convert AC to DC first at the generation point, and then convert it back to AC at the distribution point. So basically, we need converter station at the generation point and also then at the distribution point. So that can be expensive, converter stations. So we need to keep that in mind. So there is a break-even point. So considering the distance of the transmission line, basically we can with the usage of HVDC, we can save costs on transmission towers and the conductors, but then we have to spend on the converter station. So then there comes a point on this distance, as you can see in this graph. So if you move on x-axis towards the distance, the investment cost increases. So for DC, the slope is not as steep as for AC. So obviously then there comes a point around, currently it is around 600 kilometers where it breaks even with the AC, means anything longer than 600 kilometers, then DC, HVDC becomes cheaper than the HVAC. So in terms of losses, there are different types of losses when we talk about the power transmission. But as I mentioned, the DC power do not have all other losses except the resistive loss. Um, so corona loss is caused by ionization of air molecules near the transmission line conductor. So if you had the chance to visit the site which has these long high voltage transmission lines, so you might have experienced some buzzing sound like this. That is basically because of the corona losses, so that air around the conductors is ionized because of high voltage AC. Um, so basically that does not cause spark, but it is a loss of power. So because that ionization obviously results in loss of current, so you lose some power on the transmission line. And similarly, skin effect is another um, uh, type of loss in AC transmission where the AC power likes to travel around the skin of the conductor. So it doesn't travel through the core of the conductor. Basically, it likes the skin of the conductor. So obviously, if we want to send a lot of power, so then we need to have thicker conductors, right? So that obviously, if the conductor size is limited, then it can result in these losses. Uh, so these skin losses are also higher in AC power, and the reactive losses are also lower, almost zero in DC power. So this is an example here shown for 1,000 megawatt or 1 gigawatt of power transmission at 500 kilovolts over a 640 kilometer distance. So you can see that the blue one here is HVDC. So HVDC does have a slightly higher resistive loss because it is um, the conductor uh, loss, and then all other losses like reactive losses and coronal losses is almost zero for um, HVDC, but very high for HVAC. So altogether, the total loss, as you can see, is 3 times less or more than 3 times lesser than the HVAC. So we can save a lot in terms of power losses if we switch to HVDC. But then again, we need to keep in mind the infrastructure cost, and that's why we have that break-even distance. If it goes for longer distance, the more we save on losses, that can offset the infrastructure cost. So in addition to the losses and the investment cost, there are some other factors which make DC more feasible than AC for power transmission. The first one is controllability. So due to the absence of inductance in DC, because DC is just simply zero frequency and essentially has no inductance. So an HVDC line offers better voltage regulation, and it offers greater controllability compared to HVAC. So where in HVAC we know that we need to um, do a lot in terms of voltage stability. Like sometimes we need to use voltage regulators, sometimes we need to use static compensators in order to manage the voltage on the line. But with the um, DC, we don't have to worry about those controllability issues. And another thing, asynchronous interconnection. So uh, as I mentioned earlier, with AC, it is very important if we want to synchronize 2 or more networks or generation sources on a line. They need to be synchronized. So uh, because they have a frequency, right? In some countries, the standard frequency is 50 hertz, like in Australia, and in some countries it is 60 hertz, like in US. So it is impossible. In some countries, we have a mix of both. Like some of the Asian countries, they have some networks working at 50 hertz, and the other part of the network is working at 60 hertz. So then it is impossible to interconnect 2 power grids working at different frequencies with the AC interconnection, because, like I said, and then because of the synchronization issues, it is impossible to interconnect them. But with DC, we don't have that issue. So actually, in those countries where they have networks working at different frequencies, they use DC as a linkage. So a DC link makes this interconnection possible. So basically, they converted this into DC and then at the other end convert it back to AC at the required frequency. And another factor is interference with the nearby communication lines. So this is something to do with electromagnetic interference, as we know, with alternating currents. So they produce electromagnetism and electromagnetic waves, which can interfere with the surrounding systems, communication lines, which it is a big problem in the industry actually, where we have lots of equipment and there's a lot of communication between the devices. And same at a substation, there are relays and other protection devices. These days they are smart and they communicate with each other. So with the HVDC, we don't have that much electromagnetic interference as with the AC lines. So that's another advantage of DC transmission. And then short circuit current. So in long distance HVAC transmission, short circuit current level in the receiving system is high. So because we can, when there's a short circuit, it delivers a lot of current at once. So, but HVDC system does not contribute to short circuit current of the interconnected AC system, so that way we can limit the short circuit current in those systems where we need to maintain some or maintain or limit the short circuit levels because of the rating of the switchgear we use. So that is also very important. So HVDC history, I briefly touched base on the history of DC. It's not something new. Actually, the very first grid network was based on DC transmission, but at that time it was not HV, means we didn't have the capabilities to produce high voltage DC. So that's why there were limitations. But even the high voltage DC transmission is not something new. It has been implemented in different parts, not at that level as HVAC, but still it has been used for some systems. Like you can see the examples here in Sweden and in Germany. They have used HVDC from several decades now. So over the last 40 plus years, DC projects have shown to offer significant electrical and environmental advantages um, when transporting power across long distances. So Soviet Union also had HVDC link between Moscow and Kashira. And they have this 100 kV 20 megawatt system between Gotland and mainland Sweden in 1954. So the longest HVDC link in the world is currently in China. That's linking the Xuangjiba to Shanghai. That's a more than 2,000 kilometer line, and it is working at around 800 kilovolts. It delivers power more than 6 gigawatts. So that's basically trans transporting power from the dam in Xiangjiba to Shanghai. So that's another very good example of how HVDC can be used with different power generating sources. So early in 2013, the longest HVDC link was the Rio Madeiro link in Brazil, which consists of two bipoles of 600 kilovolts. So bipole is a type of HVDC. So we'll discuss later on the types of this HVDC. So that delivers more than 3 gigawatt power connecting Port Velo in the state of Rondônia to Sao Paulo, where the length of DC line is more than 2,000 kilometers. So that's a bit about history. There are projects already in place where we have the demonstrated use case of HVDC. So it's not something completely new, but with the development of these more renewable energy projects, we are realizing the importance of HVDC now. So currently there are more than 20 DC transmission facilities in US alone, and there are like around 35 across the North America grid, as you can see in this map. So all those green lines connecting different states, they are high voltage DC transmission lines. So that's just for US in this case, but there are some projects under development in Europe, and there are some in Asian countries as well. So this again shows you the portfolio of the projects under development, and they are going to use HVDC for power transmission. Excuse me. So most of them are the clean energy or renewable energy projects. In most of the cases, they are wind farms. And some of them are offshore wind farms. So in case of offshore power transmission, HVDC is very, very advantaged as compared to AC because that can be used as a submarine cable. So instead of having overhead lines, we can use DC cables as submarine cables. Uh, Whereas with AC, it is not quite possible to have submarine cables for power transmission because there are some issues of uh, inductive resistance, so that can cause a lot of leakage. So that will not be very feasible. So in terms of technical advantages, some of them we already discussed. So HVDC has some other technical advantages like no skin effect. So as I mentioned earlier, in AC we have the skin effect where the power is um, transmitted on the skin of the conductor, not the core. So basically, we need to have a larger cross section if we need to send more power. Um, but in DC, the current is distributed uniformly over the whole cross section of the conductor. So basically, we can make the conductor size smaller. So that's a very effective way of saving cost as well as it improves the maintainability. Obviously, if you have thinner conductors, so you don't need to worry about those sag and swell due to environmental conditions. And lower transmission losses because it requires only two conductors, so power loss in DC line will be less compared to AC line. And voltage regulation, we already discussed that we don't have any inductive reactance in DC, so there's obviously uh, not much requirement for voltage regulation. Whereas with AC, we need to, after several distance, we need to have some kind of voltage regulation to keep it at a constant or relatively constant voltage. And surge impedance loading, so long EHV lines, extra high voltage lines are loaded to less than 80% of a natural load. But we don't have to, because in some cases we have these uh, loads which can have surge requirement, means that when they start up, they need more current than their normal operation. So that's why we keep a margin of 20%. So we don't load the lines more than 80% or worst case 90%. But no such condition is applicable in HVDC transmission, means we can make full use of our conductors and we can load them to maximum point. And similarly, line loading limit, there's no line loading limit for HVDC line. So the permissible loading limit on AC lines are limited by the transient stability limit and the line reactance to almost 1/3 of thermal rating of the conductor. So um, those of you who have worked in power system industry, so you must know that whenever we design our system or cable design, we calculate the line loading that is to do with the thermal limit of the conductor, um, because um, if there's high current flowing through the conductor, it can raise the temperature, and there's a limit for how much we can load a specific size of conductor. But with DC, we don't have to worry about those line loading limits because there are essentially no losses. So lesser coronal loss and radio interference, we already discussed that the coronal loss is absent in DC lines, and DC obviously do not have electromagnetic interference. Um, with the DC, we can achieve higher operating voltages. So design of installation of conductors for high voltage transmission lines depends on switching surges, but not on lightning surges. So the light level of switching surge will be less in DC line compared to AC line. So that means we need less insulation in case of DC line, or in other words, we can say that we can achieve higher voltages on a DC line as compared to AC line. Similarly, reactive power compensation is another important factor where AC will require a lot of reactive power in some cases because of the power factor. And so this is because DC line does not require that reactive power compensation devices because there is no charging current and power factor operation in DC. So power factor is only applicable to AC systems. So yeah, next then we talk about some components, some major components in HVDC transmission and their working. So this is a typical circuit diagram of and the schematic of HVDC transmission. So as you can see, we can have AC generation, and then we can convert it to DC. We can use transformers to step up and then convert with at these converter stations to high voltage DC. And so we use some filters and capacitors, or this is also called DC link, to just stabilize the voltage and then send over long distances. And then at the receiving end, we need another converter station to convert it back to AC, and then transformer to step down the voltage and then send to the distribution lines or AC bus to the facility. So that's the typical um, line diagram of a high voltage AC transmission. So basically we convert this AC to DC and then back to AC at the application side. So HVDC transmission utilizes converter stations at either end of the system. So we have these mercury arc valves we used to have in the past, but more modern systems, they use these thyristors, which are solid state valves. So they are used for conversion of AC and DC currents. So the valve at the beginning of system converts this AC to HVDC, and then HVDC travels to the next location through the wires or conductors, and then valves at the end of the system convert this HVDC back to AC, and we can use it in our homes, offices, or industry, or wherever we'd like to use it. So converter station, as we discussed, is the major cost factor in HVDC transmission because a lot of work is done at the converter station. That's where we step up the voltage and then convert it to high voltage DC, and then that's where we maintain the power quality as well. Like we have filters there to convert to get rid of any harmonics or ripples. So the terminal station substations which convert an AC to DC are called rectifier terminals, while the terminal substations which convert DC to AC are called inverter terminals, right? So when we convert DC to AC, it's inversion process. So every terminal is designed to work in both rectifier and inverter mode, means the power can flow both ways, not just one way. So that's why um, we can use it for these renewable energy projects where power flow can be both ways. So each terminal is called converter terminal then instead of rectifier terminal or inverter terminal, because that terminal can essentially work both ways. So it can be a rectifier or an inverter as well. Um, so a two-terminal HVDC system has only two terminals and one HVDC line. So one terminal at the sending end, and then the one terminal at the receiving end, connected by a line. So that's all we need for HVDC transmission. Um, so converter unit is a solid state device. As I mentioned, modern systems are based on solid state switching. So if you are going to study with EIT, so EIT has a very specialized unit on power conversion systems where we teach about these switching mechanism, how we can use for rectification and inversion process. So the conversion from AC to DC and vice versa is done at these converter stations by using these bridge converters. So these are three-phase bridge converters, basically taking in AC power and converting it into one combined DC output. So it is normally a 12 pulse output because of the positive and negative on each phase. So that will produce like 6 pulse output at the DC side, right? So this is called a 12 pulse bridge converter. So because we use two of them, so 6 in each converter unit. So the converter obtains by connecting two of these 6 pulse bridge in series. So that becomes like a 12 pulse bridge converter. So this process is very simple. We control the switching to convert AC power to DC power. So that control is done by different modulation techniques. So converter valves. So these are called valves or switches. So they are the same thing. So as I mentioned, we use thyristors or IGBTs or IGCTs these days as electronic switches. So basically, these are these valves which open and close, and then that way we can convert AC to DC. So the modern HVDC converters use 12 pulse converter units. The total number of valves in each unit is 12, right? And the valve is made up of series connected thyristor modules. So we use thyristors or IGBTs because they are controllable, means we can control their switching on and off. The number of thyristor valves depends on the required voltage across the valves. So these valves are installed in a valve hall and they are cooled by air, oil, water, or freon. So we have some kind of cooling mechanism because um, of the switching on and off, as these are not ideal valves. So ideally, it should be lossless switching from on to off, but because practically they have some delay time in terms of switching off and on, they will have some loss. So that loss obviously results in heat generation. So that's why we need some kind of cooling mechanism in those halls. So because it is working at a very high power, high voltage, so that's why we need some cooling mechanism. So then we have converter transformer. So basically, as we know, the transformer purpose is to step up the voltage. So we can step up to a certain voltage and then convert it directly to DC, and that it becomes high voltage DC, and then we can transmit over long distances. So this is an image of the world's first 1100 kV. So basically 1.1 megavolt HVDC transformer is recently introduced by Siemens. So the converter transformer converts AC networks to DC networks or vice versa. So they have two sets of three-phase windings. So basically that can work both ways. So AC side winding is connected to AC bus bar, and the valve side winding is connected to the valve bridge, right? That the valve bridge we discussed previously. So these windings are then connected in star for one transformer and delta to another. So that's way we can have conversion from one type power to another. So AC side windings of the two three-phase transformers are connected in stars with their neutral grounded. The valve side transformer winding is designed to withstand alternating voltage stress and direct voltage stress from wall bridge. So because it will have one AC side on one side hand and then the DC or the valve bridge on the other side. So it needs to be able to tolerate the both type of stresses like AC and DC stresses. So it's a very sophisticated technology. I mean, there are a lot of companies working on those systems, and it's very exciting to see these outcomes like this transformer. So that's first time we have been able to produce a transformer of this size. So that's very exciting. So this shows you a single line diagram kind of illustration for HVDC converter transformer. So as I mentioned, for AC system, normally we have some harmonics issues. So that's why we use AC filters at the AC side to just clean up the power. And then we have rectifier bus where the AC system, they can be multiple AC systems. So that's the purpose of bus, to take in multiple inputs. And then we have this converter transformer connected to the valve bridge, and that will convert this AC to high voltage DC power. And in some cases, we use the DC side filter as well, just to make sure that there are no DC ripples and harmonics in the outgoing power. And then at the receiving end, same, we have a converter station with the valve bridge and the transformer, and then the AC bus to take the power away. Um, so that way we can have HVDC transmission. So the filters, there are two types of filters as we just saw, the AC filters and DC filters. So AC and DC harmonics are generated in HVDC converters because of the switching. So that's one drawback of switching to convert one type of power to another type, that it can sometimes introduce harmonics. So AC harmonics are injected into the AC system and DC harmonics are injected into DC lines. The harmonics have several disadvantages, as you may already know, that it causes interference in telephone lines. There are power losses because of the harmonics, and sometimes it can also damage the equipment we use, like transformers or the motors or other type of appliances used at the user end. And that can also cause instability of the controls of the converter. So that's why we need to get rid of harmonics. So AC filters, I'm sure you know about AC filters because they are very widely used these days, and also in the past, several systems utilize this type of RLC circuits to work as AC filters. So they offer low impedance to harmonic frequencies. The AC harmonic currents are passed to earth because they are grounded. So they can be tuned or damped, both type of filters. So AC harmonic filter also provides a reactive power required for satisfactory operation of converters. So that's another advantage of using filters, that sometimes we need reactive power to operate these converters, but as we know, DC power doesn't have a reactive component, so that reactive power can come from these filters. So similarly, we have DC filters. The DC filter is connected between pole bus and neutral bus. So pole bus is that which is the DC line is called a pole in HVDC transmission lines. It's not the actual pole like in AC. The, the pole is the tower or the pole which carries the line, but in DC, pole has a different meaning, and we'll see later on. So it diverts the DC harmonics to Earth and prevents them from entering the DC lines. So this type of filter does not require a reactive power because DC line does not have a reactive component. So this is simply taking DC harmonics from the line and injecting it into the ground. So the reactive power source, as I mentioned, some of the components in DC transmission require the reactive power. So that reactive power has to come from somewhere, right? Because DC doesn't have a reactive component. So as we mentioned, these filters can provide that reactive power. So AC harmonic filters provide reactive power partly, and some of it can come from the capacitor, the shunt capacitors directly. So the additional supply may also be obtained from shunt capacitors, synchronous phase modifiers, and in some cases we use STATCOMs, static var compensators, to provide some reactive power support wherever required. And the choice depends upon the speed of control desired. So like in some cases we may need a lot of reactive power, in some cases we need less reactive power. So we may not need STATCOMs, or some cases we must use STATCOMs. So it's different for different use cases. So similarly, we can use smoothing reactors for DC transmission. So it's an oil-filled, oil-cooled reactor having a large uh, inductance, and so it is connected in series with converter before DC filter, and can be used for both neutral line or the line or the pole line. So these smoothing reactors, they basically work like the filters. They get rid of harmonics and DC ripples, and they can limit the fault current also in the DC lines, and then can also prevent some commutation failures like in the switches, um, because they can help in terms of smoothing the switching operation. So we don't need to have very rigorous switching. So obviously, if we have high frequency switching, there are more chances of switch failure. So these smoothing reactors will ensure that the switching is not very rigorous. Smoothing reactors reduce the steepness of voltage and current surges from DC line, so the stresses of the converter valves and the surge diverters are reduced. So then there is no sudden increase or surge in the voltage or current if we use these type of smoothing reactors. So the pole, as I said, is has a different meanings in terms of HVDC transmission. So pole is actually part of the line in HVDC transmission. It's the conductor which carries the DC power is called the pole in HVDC transmission. So it also interconnects transmission lines which during normal operation condition exhibit a common direct polarity. So this pole comes from polarity. So the word pole refers to path of DC which has the same polarity with respect to Earth. So that's the meaning of pole in case of HVDC transmission. So the total pole includes substation pole and the transmission line pole. So it means at the converter station and then the whole of the transmission line that will be part of the total pole. So then we have these different types of HVDC transmission. So different types have different advantages and disadvantages. For some applications, we use one or the other. So monopole and bipole and back-to-back multi-terminal systems and tripolar. So these are the types we have so far, depending upon the use case. So monopole, as the name says, it has one single pole. So basically just one pole to carry the DC power. So it has a single conductor of negative polarity, means the power can be transmitted from one end to the other, but it doesn't have any return path. So it uses Earth as a return path. So we don't need to have a separate conductor for a return path. So for very, very long distances, this option is very useful because we use only one conductor to send power, and then we don't need another conductor for the return path. So in monopolar links, the two converters are placed at the end of each pole. So then we just need two conductors and one pole. So earthing of poles is done by earth electrodes, which are placed about 15 to 55 kilometers away from the terminal stations. But this link has several disadvantages also because it uses earth as a return path. So it can have some challenges in terms of the power, how much power we can transmit over this monopole. So it's not very much preferred these days, and so we have these type of bipole links which are more useful for long distance and high power transmission. So bipole, as the name says, it has two poles, so two conductors. One is positive and the other one is negative to the earth, means one is like a return path. So the link has converter station at each end. The midpoint of the converter stations are earth through electrodes. So as you can see in the illustration, the midpoints of each converter station on both sending and receiving end, they are grounded. The voltage of these earth electrodes is just half the voltage of the conductor used for HVDC transmission. So this way we can essentially increase the transmission power. Um, so the most significant advantage of this bipolar link is that if any of their links stop operating, the link is converted into monopole. That's another major advantage, that even if it's like a redundancy. So even if one pole is broken, we still have another pole which can work, because then in that case it will use earth or the ground as the return path. So half of the system continues to supply the power. So this type of links are commonly used these days in HVDC systems. And similarly, we can have polar links. So it has two conductors, but they have same polarity. So usually they have negative polarity and always operate with earth or metallic return. So in this case, the poles are operated in parallel, which reduces the insulation cost, means we can again send more power over this. So HVDC, as we discussed, is becoming very popular because it can be used for all these sustainable applications, especially with renewable energy systems. So we can send bulk power, like very, very high power on these transmission lines and offshore wind farms, remote land-based wind farms, and solar farms. So we can use HVDC to send very high power over long distances. So especially in countries like Australia, where we have vast land, we can develop these renewable energy projects in the middle of nowhere and then can send or transmit power to long distances without considerable losses. So some applications in offshore converter stations where we can build this type of converter stations in the sea, and we can have offshore wind farms, and then we can just transmit HVDC through marine cables through the sea. That is a very efficient way of transmitting power. So in Europe, there is a lot of focus on HVDC used for offshore wind farms. So offshore DC grid, this is shown here. So all these links are part of offshore DC grid connecting different countries. So this is European Wind Energy Association. So all these wind farms can be connected to send power. So in conclusion, these HVDC transmission grids can be optimized and controlled to support this energy transition, the renewable energy generation into the grid, because we are having challenges with AC grids that they cannot take in a lot of the renewable energy. So it can also be useful for offshore oil and gas platforms where we can supply power through HVDC marine cables, and we can have several sustainable solutions in this case. So there are technical challenges, but main concern is around the international regulations to manage the grids for the future. Um, So there is definitely a lot happening in HVDC domain, and there will be more transformation in near future. All right, so thank you very much. That's all from my side, and I'm sorry I went a bit over time. I will quickly hand over to Barry and let him finish, and then we can have some question answers if there is time. Over to
Thank
you,
you
Barry.
very Thank you very much. Thanks everyone again. Yeah, so just going in the last few slides. So yeah, so if you want to learn more on our or to see our upcoming programs, so you can go on our website www.eit.edu.au. So that's when you can view our upcoming programs for 2024. And then as well as should you want to see our upcoming webinars as well, you you can go on the webpage, and as well you can see that we've already listed introduction to safety systems, which is happening on the 17th of January. So you can just go there and do your registration. And as I've highlighted this in the beginning, that I'll be sharing the slides. So for those who can be able to scan the QR code, you can go ahead and request your certificate of attendance. For those who aren't able to, I'm just going to quickly put the link in the chat box. So if you can just follow that link to request your certificate of attendance. And then yeah, once again, for those who are able to scan the QR code, you can go ahead, and then the link again, I'll just post it in there as well. And then another thing is, just note that you've got until this coming Sunday, the 17th of December, to request your certificate. Should you not be able to do it on the 17th, or you do it after, unfortunately we cannot be able to assist you. So just ensure that you request the certificate. One more time, I'm just posting the link once again, and then for those who are able to scan the QR code, you can still do so. I'm just going to quickly check if there are any other questions. All right. Lecture, I think we should be fine at this moment. I don't see any question. Thank you, guys. Thanks, everyone, for joining. Thanks, Doctor. Have a great day.
Yeah, thank you very, and thank you everyone. Thanks for your appreciation. If you have any follow-up questions, you can send them to Barry, and I will try my best to come back to you soon.
Thanks very much. Bye.
Thanks, guys. Bye.